Hello, my name is Connor Clausen. This is my differential equations final assignment for Professor Garlick's Spring 2026 differential equations class. I already have done this a couple times, but they keep ending up too long. This is a pretty fun assignment, but I'll try to rush through it so we don't end up taking up too much time. So my data collection method, I just decided to measure like drainage basically. That was the thing I was trying to model. I ended up buying a container from Goodwill, drilling a hole in the bottom, and setting it on a scale to measure the weight at every single point. So issues with the experiment, I initially was actually going to measure height at different points. You can see me, shakily trying to mark at, 5-second intervals on the container there. I ended up just going with the scale measurement as it's a much more quantifiable, result, and it doesn't have shaky hands like I do. So yeah, that's what we ended up going with, and it ended up producing pretty decent results. I'm pretty happy with what we ended up with. But another issue we ended up having was my data wasn't behaving. It wasn't doing what I wanted it to do, which was giving me kind of a decaying relationship. It sort of is decaying here, but higher up on the graph, or if you have more water, it's actually more of a linear relationship than you would think. I think this has something to do with kind of a maximum flow rate that you can kind of have. I'm sure it just kind of levels off. I'm not exactly sure of the science there, but we ended up getting what we wanted here. This is a nice, pretty graph. I like the way this turned out. And this just resulted from me putting less water in the container to begin with. And this is a quadratic decaying behavior. And like I said, exactly what I was looking for. So setting up the actual problem here, what are we looking to find? I think that's kind of the important question to establish early on. And we're looking for a rate of change, obviously. And what is our rate of change? It's going to be the rate at which we are decreasing in volume, because the measurement I took was in milliliters. I probably should have said that earlier. Rate of change here is just going to be area of hole times velocity of water. I think that makes sense. You have your size and you have a amount flowing through that hole at every point. So multiplying it, I think it makes sense that that would give you your rate of change. So finding the area of the hole is pretty easy. I ended up kind of making an oopsie when I calculated from millimeters squared to centimeters squared. Instead of, dividing by 10, or dividing by 100, I divided by 10. Kind of a classic blunder there, but we ended up getting it fixed after struggling for a little while. So I say it's easy, but apparently not that easy. But for velocity of water, there's actually something called Torricelli's theorem, which is basically the theorem for getting the velocity of an idealized liquid through a hole. And that is this guy right here. So we end up plugging in gravity, obviously, right there. And then for height, I didn't measure height. Like I said, I measured volume. So you just convert using, we know this relationship here. So convert H to V over A, and then plug it into Torricelli's, and there you go. And there's, all the actual calculations back here that you can't see because I'm, covering it up with my face. But yeah, let's. So putting it all together, we end up kind of calculating what we can calculate here. This side being our, you know, area of the hole, and this being our like velocity. So we can take all of those constants, multiply them together, and we end up with this little number right here, just simplifying the equation quite a bit. And we throw that negative out in front actually because my measurements were negative as I zeroed the scale to begin with. And we can't put a negative in the square root, so we just throw it out in the front. So a quick side quest, since I didn't measure the water to begin with, kind of silly, we actually used the vertex formula on the equation that Excel gives us to get a vertex in seconds right here, and we plug that back into the equation to get our starting volume. We can then plug that into the IVP that we find here. This is actually a separable equation, which is kind of nice. So we just separate the variables. We get this beautiful general solution, plug in our goodies here, and then we get our solution. So our solution, when you compare it to the actual graph, which is the one on the right, well, it's the blue one on the right, Ours is the black one. So it's, kind of disappointing. Does not model it correctly, but you could actually probably guess that this is what we were going to end up with, as we didn't account for friction. Torricelli's is an ideal liquid, so everything's perfect. In the real world, that's not a thing. We have to account for things like friction, viscosity, and something called the vena contracta, which is actually really cool. I would recommend looking that up. It's basically like the pinching that comes out of a faucet. But all we have to do to account for this is just solve for like a k value, which is just doing our time theoretical over our time actual, and then we get our k value. We can plug that in, and then it matches. The red one that you see flashing here is ours, and the blue one is the original. It's a perfect match. So this ended up being perfect. It worked out a lot better than I thought it would. Thank you.